Okay, welcome to chemistry class. So we're going to teach you chemistry here, and this is just the very beginnings of the chemistry. So a lot of this information you might already know, but that's all right. It's good to get a review, and if you don't know, it's important to learn the fundamentals to get started. So why don't you tell me a little bit about yourself? Who are you?
I'm Fred.
Oh, nice to meet you, Fred. Why are you taking this class?
I need it for my major. I'm going to be pre-med.
Oh, pre-med. That's great. Excellent. What do you think? Are you scared of this class?
No, I had chemistry in high school. I know this stuff really well.
Oh, that's good. That's good. But I want to remind you that it's always okay to ask questions, right?
Yeah, I'll ask.
All right, excellent. If you something you don't know, make sure you ask. All right, so let's get started. We're going to start kind of just with a little bit of review. I'm sure most of you guys have heard of the scientific method, but the scientific method is a cycle. That's the one thing I want you to recognize. It's a cycle of making observations and then making conclusions based on those observations. And sometimes we call that conclusion a hypothesis because in a way it's the beginning of a new experiment. So if you have some experiments that you've done already and you make some conclusions, your conclusions obviously might not be correct. It's what you're concluding based on what you understand. So those conclusions will prompt you to want to perform more experiments. So when you perform the experiments and you observe again and look at the data again, then you make new conclusions and decide to perform new experiments based on those conclusions. So this is cyclic in nature. And as we go around this cycle and over, we get what we call models to help us understand something, to help us understand things like the atom, which we have found a lot of great things coming from our understanding of material, the atom, how to manipulate and control what's going on and understand nature. So that's what we are attempting to do here. Understand nature so that we can appreciate it, but also do the kinds of things that will improve lives around us. So we want to understand what a model is. We never want to feel like the model is the truth, because it's not the truth. It's simply a model to help us understand what's going on. So here's an example of a model here, which we called the plum pudding model of the atom. The plum pudding model started with knowing there was some positive and negative charges based on a handful of experiments, which we'll talk about later. But this model wasn't correct, but it answered questions, and it allowed people to explain to each other what was going on at the atomic level. And so theories are tested explanations that over many sets of experiments, models work. And so theories kind of are a combination of multiple models to explain what's going on. The word theory sometimes means, oh, it's just a theory. We don't really know. But not generally. Generally, theories are accepted sets of data and understanding that people will use to make new predictions. Once you get a small slice of understanding and you can create what we call a scientific law, then you'll get a very tight equation. So our model of the atom has changed over time, and this is probably what you're more familiar with in terms of the model of the atom. Are you familiar with this?
Yeah, I know what that is.
Okay. What do we have in the middle? What do we call that?
The nucleus?
That's right, the nucleus. And then around the outside, do you know what these little things are here?
Those are electrons.
Very good. Now, do you remember what's inside the nucleus?
Protons and nucleons.
Protons and what?
Ne-
They're neutrons. Neutrons.
protons and neutrons.
That's right. Protons and neutrons. Very good. So protons and neutrons, and on the outside we have electrons. So we have our nucleus on the inside with protons and neutrons, and the protons have positive charges, the neutrons don't have a charge, and the electrons have negative charges.
Yeah, I remember that from class.
Okay, good. Excellent. Now, let me show you this video that kind of talks about this idea of having a model for the atom. All right. So why do you think that they made that video?
They wanted us to know what an atom looks like.
Okay, that's true. They wanted us to kind of recognize what an atom looks like. But did you notice that at the end, when we were looking at what the atom really looked like, we couldn't really see anything?
What do you mean?
Well, the last shot where they were showing us the whole park and trying to explain to us the distance between the proton and the electron, that wouldn't help anybody to show them that and say, this is the atom.
So what?
Well, I think what they were trying to do here is they were trying to show us that models are fine and help, but oftentimes models aren't completely correct. And if we have something like this as our model, if something doesn't fit it in the future, if we find new things or understand material or chemical changes differently than what our model fits, we don't throw out necessarily our findings. We try to make sure that our data is not incorrect, but we also recognize that models are just models. They can't always be explained, and they can't explain everything. I mean, they can't explain everything, and we can't always explain why our data doesn't fit in them. Okay? So, the last thing you want to do is force your data to fit a model, right? You want to make sure that you don't change data just to fit a model, for example. So models are good, but they have limitations. Here's an example of our scientific law, right? That we talked about, pressure being related to volume. And here you see the balloon getting larger because we're pulling a vacuum. We're getting rid of the pressure inside there. And so there's this relationship between pressure and volume. As the pressure goes down, the volume increases. So that's a really small slice, but this scientific law is very powerful, right? Because that equation will always be correct. Okay, so matter. Matter, we say, is anything that has mass. Anything that has mass. And mass is different than weight, but it's almost used interchangeably a lot, and we forgive people who say weight as opposed to mass, but we want to try to get ourselves to say mass because weight is really a force which is dependent on the gravity. For example, if I'm on the moon, right? If I'm on the moon, well, let's start off on Earth. Here's Earth, and here's the moon. If I'm on the Earth and I'm on a scale, let's say here's my scale, and if I stand on that scale, there I am standing on that scale, okay? And let's say it says I weigh 600 pounds, right? If you take that same scale to the moon and stand on it, do you know how much it'll say you weigh?
The same?
No, it's going to say less.
Oh yeah, less, because there's less gravity on the moon.
That's right. It's going to say that there's less, you weigh less. The way these scales work is there's a spring inside, and well, not all scales work exactly this way, but in general, a scale works using the force of gravity to move a spring, and the movement of that spring tells you how much weight you have, right? So if you're on the moon, the scale would say 100 pounds, which is 1/6 of the weight on the moon, okay? Now, let's show you what a balance would do when we're on the moon and the Earth, right? So if I'm on the Earth and I have myself standing over here and I have my mass that I need to balance there, this mass would be our 600 pounds. If I was on the moon, however, and I was doing the same thing, what do you think? Would I have the same mass?
Well, probably not 100 pounds, because you wouldn't ask the question otherwise.
Okay, very good. Good observation. It's not 100 pounds. It's going to be the 600 pounds. Because here we have this same size of arrow, the same amount of force pulling down, and here we have a smaller force pulling down on the moon. Okay? So, when you go to the moon, you do lose weight.
What do you mean?
Well, you weigh less according to a scale, but you don't actually lose mass.
Oh yeah. So do you get skinnier?
No, you don't get skinnier, right? But, you know, that's what we mean when we say on Earth, I lost some weight. Good observation. Okay, that is a great start. Hopefully you've remembered some of this, and this is a little bit of a review.